You want to ask a question about the exercise?
About the second one.
Yes.
I could not do it.
So remind me which was the second one?
How to find the numeric forms for the gamma matrices.
So the way to do it is, you're given a basis. So the basis is, let's do just the one with just 3, n equals 3. Probably I should have done it. We have these different possibilities. So these are the ones with an even number of plus signs. And then you have the ones with an odd. So this is the basis with 8 elements. So you're going to have an 8 by 8 matrix. And you know how the gamma matrix acts on each of these. So for example, gamma 1 plus I, gamma 4. It would annihilate anything with a plus in the first index, and it would take anything with a minus in the first index and take it to the one with a plus. So for example, we'll take this state to this state, we'll take this state to this state, we'll get this state. It would annihilate this state and this state. And it would take this state into this one, this one. So then you can just write down the 8 by 8 matrix which does that. Okay, and that would be this gamma matrix.
I don't know if I made a mistake, but I tried to prove the relation for the anti-commutator between B plus and B minus. And with that definition, I obtained the anti-commutator equal to 2 times delta. And I don't know if it is a choice of normalization.
So it's just a normalization. Okay, so we can check it out. But if it's just a normalization, I'm happy.
Okay, thank you.
Any other questions?
When we were doing that, we didn't know how to choose the order for the vectors.
It doesn't matter. So that's a basis choice. So you can choose it however you like, and you'll get a different matrix here, but they'll all be related by just an orthogonal transformation. So of course, you have to use the same basis for all the matrices. Okay, so just to motivate you, so there's going to be an exam at the end of the school, and at least my question, usually each lecturer contributes 1 or 2 questions, and my questions will certainly be based on the questions I'm giving to you here. And the people who do well on the exam will be invited to go to future schools. So we'll have a school in May in Sao Paulo, and I think there'll be one in ICTP. Usually there's one every year in Trieste also. So that's some motivation for not only doing the exercises, but obviously learning the material. Okay, so today I'm going to switch subjects to supersymmetry. But let me just ask one more time. Are there any questions about yesterday? So I'm going to start by just defining what we mean by supersymmetry. So we have some generator Q. So remember, we have these gamma matrices. I'm going to define some abstract algebra, and then we're going to find representations of the algebra. Okay, so I'll tell you what I mean by this. So remember, in the Weyl representation, these gamma matrices were off diagonal. So we're going to construct something which is actually diagonal. In other words, this is a matrix with just entries here and here. And the algebra is going to relate these generators, which I'll call fermionic generators, because it's the anti-commutator which is relevant, to the bosonic generator, which is just the translation generator. So of course, for SOD, n equals, let's restrict to Minkowski space. So this goes, my notation is that the vector indices always go from 0 to d minus 1, where the 0 index is the time-like index. And you can choose a representation where gamma 0 is just equal to 0 minus 1. So the square has to be 0. So remember, these are 2 to the n minus 1 dimensional matrices. And the gamma j's, we have the form 0 sigma j. So these will, I'll call these Pauli matrices. Okay, so these are 2 to the n minus 1 versus 2 to the n minus 1 dimensional matrices. So remember, n is half of the dimension. N is let's assume it's even for now. So that means when n is equal 0, this is just the identity. Right? Gamma 0, gamma 0. Oh, sorry, it's minus it. Gamma squared is just minus 1. Whereas gamma 0, gamma j, what you'll get here is just sigma minus sigma. Okay, so this is the algebra we're going to consider. And what we'll find is representations of this algebra in essentially every dimension are physically interesting. Okay, any questions yet? So far it's mathematics, but the rest of the class will be physics.
But in order to be an algebra, you need the algebra of the p's with the q's?
So let me tell you the rest of the algebra.
Okay.
So the rest of the algebra, Pm with Pn is equal 0. Pm with Q alpha equals 0, so this is a constant. And finally, you have the Lorentz generators, which I'll call M and N. So these are antisymmetric. And they transform P as a vector representation as Q as a spinor representation. So we learned what those representations were. So the vector representation is A to N P. Spinor representation is So I'm not sure about the sigma n. So this is a matrix, which has obviously. So this is how the M and Q algebra act, and of course MMN with M and Q is the Lorentz algebra that I asked you to work out in the last class. So A to N P. Okay, so I'm not sure about the coefficients, but that's the algebra. And of course it satisfies all the Jacobi relations that you need for it to be an algebra. So of course if I leave out Q, it's just what's called a Poincare algebra. So this is called a super Poincare algebra. And it has the interesting property that it's the unique generalization of the Poincare algebra which has physical representation. So of course, one can introduce internal symmetries into a Poincare algebra, but so for example, Yang-Mills has additional symmetry generators in addition to the Poincare generators. But those additional generators all commute with M and with P. So in that sense, it's a trivial extension of the Poincare algebra. This is the only non-trivial extension of the Poincare algebra, which has interesting physical representations. So that's what we're going to see now, is what are these interesting physical representations. Any questions?
You're just using the gamma zero just to make the metric block diagonal. Is there any special reason?
Well, as you'll see, this is the representation which is interesting. So what we'll see in a second is that with this definition, P0 will always be positive. You could try to construct other algebras, but as I said, they won't have any physical representation.
Wasn't the lower block sigma like the adjoint, or is it real?
You're right. I should have put in that. These are supposed to be Hermitian matrices. Okay, so let me prove some properties of this before we look at representation. So the first thing I already said, if you take, let's consider you have a state here, which I'll call a ground state, but it can be any state. And we want to compute the energy of the state. So the energy is, of course, T0. So this is the expectation value of the energy. And I probably have a sign wrong. Yeah, I think when I go to notes, so I have some notes that are, I'll try to scan them and put them online, but they have more information than what I'll say here. So maybe there's somebody here that's going to actually prepare notes for my lecture, which actually be useful. I don't know if it's possible or not, but this is essentially standard. You can learn all this in Wesson Bagger if you want. Okay, so I think I used a different metric. I used the West Coast metric. So this should certainly be plus. We'll see in a second. So the point is that this algebra implies that this object can be written as 0 times the commutator of Q0 with Q0 in effect. So this is equal to, this means that this is equal to Q alpha, Q beta, delta alpha beta. So I can take, in fact, any component of this, because this, when M is 0, this is just a diagonal, just the identity matrix. So that means if I take the commutator of any Q with any Q, I will just get P0. So I could have done, instead of doing this, I could have just taken the first component. That's also true. But let's do this to delta alpha beta. And then you divide by some normalization. So I'm not worried about the normalization. What I want to argue is that this is always positive. So the way to prove that is to write the fact, use the fact that these are Hermitian, and use the fact that this can be written as just square. Well, so if I just take this state here, Q alpha 0, and I take the square of it, then obviously this is a positive definite quantity. So we prove that the energy of any state in the theory is positive. Now, of course, that's something we want of physical theories, and it's not true if the theory is not supersymmetric. There's nothing stopping you from considering, for example, an action of the type d phi plus phi cubed. And as we compute the energy, depending on the sign of phi, the energy will either be positive or negative. So this is as far as an ordinary field theory is concerned, it's okay until you try to compute its energy and you see that it's not bounded from below. However, this theory cannot be supersymmetrized. So there's no supersymmetric version of this theory, and this is the proof. Because if there were, then you'd be able to prove that there are states for which the energy is negative. Okay, so this is a nice property of supersymmetric theories. The energy of every state positive or is non-negative. And it's 0 if and only if Q alpha annihilates the state for every alpha. So the ground state, the state with 0 energy, is a state which is actually spacetime supersymmetric. It's annihilated by all the spacetime supersymmetry. If there does not exist a state satisfying this, then we say that it's spacetime supersymmetry. If the Lagrangian is spacetime supersymmetric, but the ground state is not, then we say that spacetime supersymmetry is spontaneously broken. But if it's not broken, if the Lagrangian is spacetime supersymmetric and the ground state is spacetime supersymmetric, then that's the unique state with 0 energy. Okay, so that's something nice. Another nice property is that when you compute the spectrum, you'll find that the masses of every boson, for every boson of a certain mass, you get the fermion of the same mass. So that's also trivial to prove. So we're going to prove it in a slightly different way. We'll take trace. And we'll take a trace over all states. And suppose we want to construct, for example, trace of -1 to the f of m squared. So what this does is for every fermion of a certain mass squared, it contributes -m squared. For every boson of a certain mass, it contributes +m squared. And what you can show is that if you sum over all the states, you always get 0. Okay, so the proof is very simple. We'll use the fact that m squared is, of course, equal to Pm, which we can write as Pm. We can use this algebra to write it as so this is, of course, the same as Pm, which is this gamma matrix. So now we can just contract the gamma matrix. And there's some normalization I'm ignoring. After some normalization, this is equal to this. And now we can stick this into the trace. So this is proportional to the trace of -1 to the f, Pm. Okay, now we can use the cyclicity of the trace to show that this is 0. So the way to do that is to use the fact Q's all commute with P, so it doesn't matter if I put the P in the Q here. But they don't commute with -1 to the f. So well, let me write this as Q alpha Q beta plus Q beta Q alpha.
We need a minus there, no?
A minus where?
There, because by the definition,
Well, it's proportional. Is that
no,
correct?
but
Minus here, yes? You're right. In my definition of m squared, was a minus. But since I'm only worried about proportionality, I don't care if I put a minus sign. Okay? I'm going to show it's 0, so it doesn't matter. Once it's proportional. Okay, so let's analyze this term here. So trace -1 to the f Pm Q alpha Q beta. Let me put this to the other side because of the cyclicity of the trace. This is equal trace Q beta minus 1 to the F PM Q alpha. And now because this has fermionic number minus 1, when I pull it through here, I get the minus 1. So this is equal trace minus to the F. Now with a minus sign. Let me put the minus sign. Minus Q beta PM Q alpha. Right? All I did is use the fact that this is a fermionic object. So when I pull it through, I get the minus sign. And now you see, I have this, I can pull through PM because Q and P commute. Get minus PM Q beta Q alpha. So this term here, when I pull the Q beta through the trace, and pull it through minus 1 to the F, I come back with a minus sign, which means it's going to cancel this term. So these two terms here contribute with opposite sign, and they cancel. So it's easy to show that this is true not just for m squared, but for any function of m squared, etc. So that allows you to prove that at every mass level, you have an equal number of bosons confirmed. Okay, so why is that interesting? Well, when we compute quantum field theories, we know that we have divergences. Typically, you have divergences. And if you have bosons in fermion, if you take in a quantum field theory, of course, you know that the bosons and fermions contribute with opposite signs. So if you compute, for example, the self-energy of some, let's say this is a bosonic state, there's a contribution coming from the case when the internal state here is bosonic, and there's another contribution when the internal state is fermionic. And now the claim is that if the theory is space-time supersymmetric, of course the contribution from the loop depends on the mass of this internal state. But because of this theorem that we just proved, the mass of the boson, for every bosonic internal state, you know you have a fermionic internal state of the same mass. And in fact, I'm not going to prove it here, but that the interaction term here is also related. So what you find is that the contribution from here is cancelled by the contribution from here.
What if we consider quartic interactions?
Okay, so we can extend this to more complicated diagrams, and then the cancellation is not complete, and you might get some contribution. So of course, it's not true that all loop amplitudes cancel, but at least the most divergent ones typically do cancel. So supersymmetry does not eliminate all divergences, but it eliminates at least the most extreme ones. So for example, if people that study the minimal supersymmetric extension of the standard model, so there are divergences if you just have a Higgs boson, which gives a quadratic divergence. And once you supersymmetrize it, that quadratic divergence gets reduced to a logarithmic divergence. Okay, so this is a typical property of supersymmetric theories, which is nice. If you want to do quantum field theory, sometimes these divergences are so bad that they kill the theory. Now it turns out in string theory, you not only have superstring theory, you not only have this space-time supersymmetry, but you have more symmetries, which you'll hear about from Carmen. So when you try to do supergravity theory, they're supersymmetric. So gravity, I think everybody knows, here is not a renormalizable theory if you're in more than 2 dimensions. But we want to understand quantum gravity, of course, in 4 dimensions. So if we want to understand as a perturbative quantum field theory, we have to understand what to do with these divergences. And at the moment, superstring theory is the only theory we have which at least tells us at the perturbative level how to handle these quantum divergences. Now, you can consider supergravity theory, but that turns out to be not enough to cancel all the divergences. Superstring theory, which is of course much more restricted than supersymmetric theory. So what I'm telling you here is true for any supersymmetric theory. So it gives you some restrictions. So for example, we've learned that the energy has to be positive but not negative. but it's not as restrictive. Of course, superstring theory is a much more restricted theory. And if we want to get rid of all the divergence of perturbative supergravity, we need to go to the full string. But at least, for example, for super Yang-Mills, this supersymmetry has been very useful for studying quantum properties. Okay, so these essentially are the main motivations for studying supersymmetric theories. It gives you a restriction on a whole class of quantum field theories, or theories in general, and the restrictions it gives have interesting and nice physical consequences. If it matches our universe, we don't know that yet. Certainly as interesting physical theories, it's a subclass of all theories which seem to have better properties than in general.
For me, it seems that, you've shown that the trace of the mass matrix is 0, right?
Yes.
So for me, the case where you have an equal number of fermions and bosons is just a case of this.
Right, so this is not enough to prove that at each mass level you have the same. But now suppose I do the same argument for every function of m squared. If it's true for every function of m squared, then this argument is easily generalized. Any other questions? Okay, so these are the nice properties of supersymmetry, and now we're going to go to specific examples. So today we'll start with the simplest example, which many of you probably have never heard of, but it's probably something interesting to know even if you're not interested in string theory. Although, of course, it's a baby version of string theory. So what it's called is called the spinning particle. So this algebra, of course, can be done in any dimension. We'll find out tomorrow that above 11 dimensions, it has a problem that it implies that you have more than one graviton. So, but certainly the algebra you can write down in any dimension. So the first case we're going to consider is t equals 1, which is the case where you only have a single time-like direction. Now, it sounds silly if you're thinking about field theory. Well, it's a one-dimensional field theory. But if you think of it as quantum mechanics, it makes sense. So if I have a function, I can call it phi. This is a function of tau. And I can consider, for example, an action of this type. And I can ask how to make this action space-time supersymmetric. Now, obviously, I'm going to have to introduce some anti-commuting degrees of freedom. And the question is, what kinds of anti-commuting degrees of freedom I want to introduce. So, I'm going to call my anti-commuting degrees of freedom psi. And it will turn out that the action which is going to be space-time supersymmetric has the following form. So of course psi squared would be 0 because this is anti-commuting. But you can write down a first order term which is non-zero. And I've written it down, I've put this I here so that the factor is real. So why is this real? It's because when you take the complex conjugate, the Hermitian conjugate, what you should do is flip the order. So this is equal to minus I, because of the I. And now we flip the order, we get psi dagger, psi dagger. So psi is real. This is just equal to minus I, psi dot. But these are anti-commuting. So this is equal to I, psi dot. So if I had not put the I in here, I would have gotten a minus sign here, so it would be imaginary. instead of real. Okay, so I want this to have the same reality property as this. That's why I put the I. Any questions? So phi is just a function of tau. Later I'll give you a physical. I will phi just so you can think of it as a one-dimensional field. Bosonic field. These are boson.
Complex or real?
Real. And now I'll tell you what the supersymmetry transformations are. So first of all, let me tell you how P acts. So of course there's only one P, because you only have m equals 0. So P0 is just I dd tau. So it just takes delta phi, P with phi, just I phi, and of course psi is just I. Now I have to tell you how Q acts. Now if you remember from yesterday, in this case, we just have one component of Q. So the algebra is just Q squared is equal, in this case, I guess it's 2Q squared is equal to P0. So I have to tell you how it acts on phi and psi. And I'm not sure I'm going to get the coefficients right, but my supersymmetry transformations will be Q on phi will be I alpha or I. So I hope I get my Q on psi. So now suppose I do Q twice. Let me just so to simplify notation, let me just call this Q phi. So Q squared phi, well this is equal to Q phi is equal to I Q of psi. So that's equal to I phi dot. All I did is act on this so I have consistent notation. So I just don't want to keep writing the commutator. So when I write cube psi, I mean the supersymmetry transformation on Q. Now you can see that Q exchanges a bosonic object with a fermionic object, so obviously Q is fermionic. So Q squared of phi is Q of phi, which is I of Q of psi, which is I phi psi. Q squared psi is Q of psi, is Q of phi dot. Here we have phi, this is I. So what we've shown is that this is just equal to P0 phi, and it's just P0. Yes? Was a factor 2. Yes? Why did I define it in this way? It's a definition. I defined it this way so that I reproduce the algebra. Now what I have to show is that this transformation actually is an invariant of this Lagrange, of this action. That I haven't shown you.
Then why not Q phi equal to E
Psi dot?
psi dot?
You can define it how you like, but of course it has to satisfy the algebra. Now you have to prove to me that yours works. I can give you a simple argument why this would be better than yours, which is if you look at the dimension of these fields, you can see that psi has one less derivative, which is in phi. So that means the dimension of psi has to be half bigger than phi. Which means if you put the dot here, you would find that q in one case has a certain dimension, and in the other case it has another dimension. So this is the only one which would be consistent with this Lagrangian. Okay, so now we need to show that the action is preserved by this. Okay, that's not so hard to do. So let's compute Q acting on this object. So now there are several terms because you have Q of phi here, Q of phi here, Q of phi here, Q of phi here. So let's act on this one first. So it can either act on the first or the second one. But it's easy to see you're just going to get a factor of 2. Here it's a little bit trickier. So you get plus I, Q of psi dot, times psi. And now you need to be careful because when Q acts on this psi, this is fermionic. It has to go through this psi dot. That's going to give you a minus sign. So you get another term which is minus I psi dot. So just to repeat, this minus sign came because this is the fermionic generator. So when you pull it through a fermionic object, it has to anti-commute and not commute. So that's why you have the minus sign. Okay, now we use this definition here. And we find that it's equal to 2I psi dot times phi dot. From here. Then you have a term plus I. Q psi dot is I times phi double dot. Psi. And then finally you get the term from here, minus I psi dot phi dot. This is not 0. On the other hand, you can write it as I times dt tau phi dot psi. Now these two terms, of course, don't cancel. It gives you 2I minus I. So when the dt tau hits here, it gives you this term. And when it hits here, it gives you this term minus I. So the Lagrangian is not invariant, but the action is up to a total derivative. So in everything that we'll talk about throughout these lectures, we're going to ignore surface terms. Okay, so we see an action is supersymmetric if the Lagrangian is invariant up to a total derivative. Any questions? Okay, I wrote something down. Why is it physically interesting? Okay, so now I'll tell you why this system is physically interesting. Instead of calling this phi, let me call it x. And instead of just having one of them, let me have d of them. But not capital P, small p. So let me give it p equals 1 to d. Actually, I'm going to say p equals 0 to d minus 1. Let's see why in a second. And let me obviously put another index on the side. So this is just a sum of p terms that we had before, just a sum of 2 terms. Now it no longer looks like a field theory. It looks like some kind of quantum mechanical or first quantized action. So the only reason I called it phi before is because sometimes people get confused. They think this is space-time supersymmetry. It has nothing to do with space-time supersymmetry. What's being supersymmetrized is the one-dimensional world line. Okay? So of course all the formulas go the same. P does nothing, it just sits by itself. Now P is a space-time vector index. So the fermions here are space-time vectors. And remember yesterday I insisted that a fermion has nothing to do with its Lorentz representation. So in this case here, the fermion is not a space-time spin, it's a space-time vector. This system does not have space-time supersymmetry, it has world-line supersymmetry. It's called world-line supersymmetry. Now let me put a coefficient in front of it, action, which will be the mass. And now it looks like a generalization of just a massless first quantized particle. So the equation of motion is trivial. It's just m. So I get the equation of motion by varying with respect to x. It's the usual thing. So it just describes a free massless particle. Acceleration is 0. But there's another equation of motion coming from varying psi. And that gives the equation Im psi dot equals 0. So what is this describing? It's not just a massless particle, because it has extra degrees of freedom.
Okay.
It turns out this system is describing a spin 1/2 particle. So if you want to describe an electron of mass m, its first quantized language, the easiest way to do it is this way. Okay, so how do I convince you that this is describing a spin 1/2 electron? We can first compute the Lorentz current. So let's compute the Lorentz current as a contribution. So we can compute the Lorentz current by using the usual Noether method. This is, of course, invariant under SO d minus 1 rotations, which rotate the P index. They don't mix x and psi, they just rotate the P index. And you can compute the Noether current. And you find that Noether current is, of course, has a term of this type, coming from x dot in x. So that's the usual orbital contribution to the Noether current. But there's another contribution coming from the psi's, which is of this type. So this is the orbital contribution. And this is the spin contribution. Why do I call it spin? Well, you can compute the algebra of these psi's. And of course, these currents here form their own algebra. And it turns out that if you consider the case where the particle is non-relativistic, it turns out that psi 0 is approximately 0, non-relativistic limit. And the psi j's, the remaining ones, I equals 1 to 3, you have 3 of these, because you can either have psi 1, psi 2. If we're in 4 dimensions, you have psi 1, psi 2, psi 1, psi 3, psi 2, psi 3. I guess I should have written this. And you can identify these with the 3 components of the spin. This would be Sx, Sy, Xz. And you can easily quantize this system. Psi satisfies the usual anti-commutation relation. And you find that the spin, I'm not going to have time to do this, but you can find that this is equal to 3/4, which is of course equal to S times S plus 1 over 2, where S is equal to that. Not over 2, thank you. So this is a straightforward computation. It's in my notes, but it's a little bit going off the main content. But there's something else you can do to convince you this is an electron. You can couple it to an electromagnetic field. So everybody should know how to couple an ordinary particle to an electromagnetic field. You add the coupling term. And what that does, that modifies this equation of motion to now give you the equation of motion in Lorentz in an electric field. So you get a term here of the type E F P. So this, if you haven't seen it, you should certainly, I don't know, open Landau and Lifshitz or any book that does a particle in an electromagnetic field. And you can derive this equation just by varying the equation, this with respect to x and including the contribution from the variation of the gauge. Now this Lagrangian itself is not supersymmetric anymore because of this term. If we do this transformation, this will not be preserved. But you can add a term which is of this type. Which makes space-time supersymmetry now, it makes the world line supersymmetry not just for this term, but also for this term. So let me put the...
Sorry.
Yeah?
So these psi's are not independent moments?
Independent? These are variables, fermionic variables. I don't know what you mean by independent, but...
so is there some happy coincidence here between the dimension of the George representation and the Dirac representation?
No.
So
So
it's
let me
only-
say again, these are not space-time spinors.
But then you're making...
These are space-time vectors. We're describing an electron in first quantized language. In first quantized language, let me add a side comment, which may be confusing but may be useful. These psi's satisfy a certain anti-commutation relation. This type. That just comes from canonical quantization of this. This should remind you from yesterday's lecture of a Clifford algebra. So the psi's should be interpreted as gamma matrices.
Okay, that one.
Okay, but we don't have to think about that. We can just ask, what are the equations of motion you get from varying this Lagrange? So these are just classical equations of motion. And what we find is that by introducing this term here, which is world line supersymmetric, you get contributions, of course, here. And the contributions you get are precisely those of, let me write it down. Something wrong? So you get the contribution here coming from varying the x's here. And you also now get the contribution to the psi's. So this is no longer just psi dot equals 0. Now you get the contribution from varying the psi. Now these equations of motion here, with this identification of the spin, is precisely the equations of motion for an massive spin 1/2 moving in an electromagnetic field, where this gives you the coupling of the spin to the derivative of the, I guess the electric, well, it depends on the indices. And this gives you the precession of the spin from the magnetic field. So this is supposed to convince you that this system is really describing spin 1/2 particle.
If you take these numbers as discipline, you should get 2 degrees of freedom. You have small components and big components. How do you understand that you have the same number of fermionic degrees of freedom? And
This is a world line. So we have the same number of x's and psi's.
exactly.
We do not have the same number of space-time particles, because it's not space-time supersymmetry.
But when I
So this
describe an
describes a
electron
single spin 1/2.
in quantum mechanics, I normally have half the number of. So I have a wave function which has two components and I have a
So
position.
now you're quantizing. So you could have asked a different question. Suppose we just did the x's. Now that describes Klein-Gordon particle. Now you could have asked, how do I see the Klein-Gordon field from this action? So what you have to do is you have to quantize and then you interpret the quantum mechanical wave function as the field. You can do the same thing here, but now the quantum mechanical wave function has many components because it's a representation of this Clifford element.
And some of those are redundant?
No, they're different components. So electron has 4 components. It has the positron, the electron deal with the.
Okay.
So those are those 4 components.
I see.
Okay, so this is of course in 4 dimensions, but in other dimensions it has more components.
So F is like the field strength, but
F is the field strength. So this I should have told you that. Fmn is dm an minus dm.
Is there any way to write down that Lagrangian in terms of maybe 2p times 2p matrix regarding x and psi, perhaps? Yeah, because you have the construction of exactly p bosons and p fermions.
Yes?
So I'm guessing that perhaps I can write down that Lagrangian in terms of the multiplication of 2 matrices that concerns one part of x and one part of psi, in order to have a known expression for Lagrangians. No?
Okay, maybe we can talk later. I think I'm missing your question, but this is just an ordinary first quantized.
Yeah, I follow. Okay, I can ask.
We can ask later.
later.
I think I'm not picking up on you.
Sorry, is there a systematic way to find the action of M on the field, or is it by heart?
Okay, so I knew the answer,
Okay.
but now you can ask another question. Suppose I just know the bosonic part. How do I supersymmetrize? How do I find the supersymmetric generalization? Okay, that involves a method that I will say a little bit about, but I won't have time to discuss. This Lagrangian is, of course, manifestly invariant under this symmetry. Why? Because under this symmetry, dt tau just shifts all the fields. So as long as there's no tau dependence explicitly, you know that P0 acting on the Lagrangian is nothing but dt tau to Lagrangian, or I times dt tau to Lagrangian. So this is obviously a symmetry because it takes Lagrangian to something plus a little derivative. There's a way to make Q also manifest in the same way. What you have to do is you have to introduce a new kind of variable that goes over here, which is a fermionic. So this is bosonic. This is just the usual proper time. And you introduce a fermionic coordinate. So this is called superspace. Now what you find is Lagrangian, instead of writing Lagrangian just as a function of this x and this psi, you write it in terms of this capital X. The relation between the two is this capital X, this kind of X, has 2 terms. One term is bosonic, and the term which is linear in kappa, this is a fermionic coordinate, so you can only expand it once. Kappa squared is 0, is precisely the psi. And you can write this action in terms of these, and in that way, the action is manifestly space-time supersymmetric. Now, what I'll do is I'll write it, but I won't explain it, okay? So, because I don't have time to go into details. But you can write the action in this way, d tau to kappa. But this is just the ordinary Bayesian integration over kappa. This is the same as that. So if you know what superspace is, I'll tell you what D is. D is equal to DD kappa. You can show that this is manifestly space-time supersymmetric, manifestly world-line supersymmetric, and coincides with this. So this is the generalization of this term. So this method is called superspace. And I'm not going to have time to discuss it, but it's certainly very useful if you want to understand what the method is for constructing these Lagrange.
That is what I was asking.
Okay. So of course, a standard reference for D equals 4 is Wesson-Bagger. So there are many other references, but this is a good starting point. Okay, any other questions?
Those magnetic fields are arbitrary, or
Yes.
only mathematical?
They do not have to satisfy any equations of motion. This is world-line supersymmetric for any. Maybe I'll say, just because I will forget to say maybe later, when we do the D equals 2 version of this, that will correspond to the spinning string, which Carmen will talk about when she arrives. And in that case, what you find is you can write the same coupling term. But in that case, as you will learn in Barton's talk, conformal invariance plays an important role. So in 2 dimensions, this Lagrangian turns out to be conformally invariant under 2-dimensional conformal transformation. And it will turn out that if you ask the conformal invariance is preserved at the quantum level, it will imply that these Maxwell fields have to satisfy Maxwell's equations of motion, or more precisely, Borningfeld equations of motion. Okay, but the particle, there's no restriction on these phase analysis. Do you know this?
Small d could coincide with the number of dimensions, but could be bigger.
Small d is the number of dimensions of the space-time. I don't know. So the x's are the space-time coordinates. So in that sense.
So big D,
So I'm
the
sorry.
big D equals
So capital D is 1. Now, because there's only one tau. So this supersymmetry algebra is just this. That's it. This 0 has nothing to do with p equals 0. It's really this one here. So it's confusing. And this is world-line supersymmetry, not space-time.
One question. When you take the non-relativistic approximation, you
Yes.
said psi 0,
Yes.
0. You didn't take this approximation.
Yes.
How many spin degrees of freedom?
So you always have the same number of degrees of freedom, but these s's satisfy a constraint. So the constraint is that Sm times x dot m is equal to 0. So when x dot 0 is much bigger than the others, that forces S0 to be 0. But in the case where x dot 0 is just as big as the others, then you have a constraint which mixes the s's. So you have the same number of s's in it. It doesn't change the physical spectrum, it just makes it easier to analyze them.
Okay, but if you have 4 fields, psi 0, psi 1, psi 2, psi 3, you could in principle form 6 objects.
Yeah, you're right.
I know,
So
it's
I
gonna be
said
a
it
limit.
wrong. So what I should have said is, sorry, psi m. Thank you. The correct thing is psi m x dot n. So of course, psi, that implies psi is 0. One of the psi's is 0. So that's what
I have a question. In the normal action, when it's not supersymmetrized,
yes.
and also in the non-relativistic, this problem is related when you quantize with the Landau level problem.
Yes.
So there is some unusual way how the spectrum is modified when you supersymmetrize the theory in the non-relativistic.
I don't. So I'm not familiar with what you're talking about with the Landau levels, but I think this will just give you the Landau levels with spin 1/2.
Okay.
I think there's nothing unusual. This is these equations of motion are the right equations of motion, so it should give you the right mechanical system. But yeah, I have never studied that, so there might be some subtlety that I'm not aware of. If there is, maybe tell me after the class.
What I would say. What does psi n dot n equals 0 come from?
Where does this equation come from? Where,
No, the constraint.
so it comes from, oh, where does this come from?
Yes.
Okay. So if you do the massless particle, or if you do the massive particle, and you write it in reparameterization invariant form, the reparameterization invariant action is this, right? It's x dot m times n. Okay. Now, if you start with this Lagrangian and you canonically quantize, or you look at the constraints, this turns out to imply that Pm, the canonical momentum, satisfies this constraint. When you world line supersymmetrize this, you get also a version of this type. Now, I'm lying a little bit because I don't want to go into details. This is really for the massless case. This equation here is the same. When you write the world line supersymmetric version of this, you get a constraint. The momenta are not independent of the size. And this constraint here is related to the Dirac equation. So the same way this is related to the Klein-Gordon equation, this one, when you use this quantization condition here, it just becomes Pm gamma m equals 0, which is just the Dirac equation when you interpret this as a restriction on the wave function. So this constraint here is essentially the massless Dirac equation. So in order to see this, you have to go back to the world line reparameterization invariant action. It's a bit of a mess. That's why I started. This is already in the gauge where, what's it called? Where you identify. I'm not going to say that. Yeah, you identify in the gauge where x dot. You can fix the reparameterization invariant by defining x dot m equals 1. So this fixes the parameterization of tau. And that allows you to write it in this simple form. Okay, but these are details that I don't really want to do. Any other questions? Okay, so now we're going to do the equals 2 version. So it's not very different, fortunately. And then tomorrow's lecture we'll discuss the equals 4 and higher dimensions. So t equals 2 means we're now going to have tau, but also sigma. Okay, the same tau and sigma divided into 2. And of course, if we want to have world line supersymmetry, we also need the psi. But now we have a question: how many psi's do we need? Okay, so obviously now we're going to have because remember, when d equals 2, there are 2 different q's. Let's do it in 2-dimensional Euclidean space. Now we can do it in both. But remember, in this case, n equals 1. So we just have this object. It can either be plus or minus. So that's the spinner. If you're in Euclidean space, this is the complex conjugate of this. If you're in 2-dimensional Minkowski space, each of these are independently real. So in most cases, when you do the spinning string, you consider 2-dimensional Euclidean space. But you can also consider 2-dimensional Minkowski space. And in that case, there is a possibility of just having one of these. So in Euclidean space, you have to have both. In Minkowski space, you can just have one. And when you discuss the heterotic string, I don't know exactly when you'll hear about it, the heterotic string only has one of them. But what's called the type 2 string, which has both. Okay, so we're going to have Q plus and Q minus. And we also, of course, have P0 and P, or P tau and P sigma. You can have P tau, which is PD tau, or IDD tau. P sigma, or IDD sigma. And it will be convenient to construct a combination, which I'll call P plus and P minus, where this is equal to I ED tau plus I ED sigma. This is equal to I minus. Okay, so this would, I don't think Barton has done complex coordinates yet, has he? So when you go work in conformal gauge, you've heard about static gauge and a little bit about light cone gauge, but eventually you learn about conformal gauge, and which is very convenient to combine tau and sigma into these complex combinations. And the algebra will be Q plus with Q plus. In my notes, I have nothing like this, so I'm not sure about that. And Q plus with Q minuses. So actually, I'll give you an exercise. Show that this algebra here is related to the algebra where these sigmas Pauli matrices. Sigma 0, these are 2 by 2 matrices. Okay, so show that these two are related. So it's just a change of basis, but it will allow you to get used to this notation. Okay, so now we want to modify this. So I'm not going to have time to discuss the coupling to a background field. But I'll just tell you that it generalizes in a nice way. Now we're going to world sheet supersymmetry. One more thing I could have answered to the question about psi m x dot m. When you do the strings, as you will see with Barton, in conformal gauge there's a constraint of this type, which is right to choose a conformal gauge. And when you construct the world sheet supersymmetric version, there's a fermionic superpart of this, which is of this form. And this constraint here is just the world line version of this world sheet constraint. So that's another way to think of it. This comes from world sheet superconformal invariant. This is the world line generalization. Okay, so now we want to generalize this action for the string. So first we have to decide what the starting point is, and the starting point will be the bosonic string. So it's convenient to write this in conformal gauge. So the Nambu-Goto, I'm not going to do Barton's talk, but the Nambu-Goto action, if you go to conformal gauge, has a simple form. It's just d plus x d minus x, where d plus is d tau plus I d sigma, and d minus is d tau minus I. So now this is just the ordinary bosonic string action of conformal gauge. Now I want to supersymmetrize with respect to world sheet supersymmetry. So we have xn. And we have to figure out what's the world sheet. How did it transform under world sheet supersymmetry? Well, we have two different world sheet supersymmetries because we can act with q plus or with q minus. We can consider q plus of xn and q minus. And we're going to find q plus of xm to be equal to I psi plus m, and q minus of xn to be I psi minus. So we have for each index m, which goes from 0 to d minus 1, so the same. We have two fermionic coordinates, psi plus and psi minus. The reason why we have two is because the spinner, these are world sheet spinners, space-time vector. It's a world sheet spinner because you have world sheet supersymmetry. So world sheet spinner means it has either plus or minus component, this plus or minus here. But the space-time index is the same as x, because the world sheet supersymmetry does not act on the space-time index. And now I have to tell you how q acts on the side. So the definition is going to be q plus of psi plus is equal to d plus xm, q minus psi plus q minus psi plus m is 0. Then we're going to have q plus psi minus m is 0, and q minus psi minus m is minus m. And probably I need i's. No, I don't. So those are the definitions of the supersymmetry transformation. Doing exactly the same analysis as we did for the spinning particle, one finds that q plus squared on xm is equal, we can do it in our head, q plus of xm is I psi plus m, and now we have this q plus again, that comes in here, so we just get I d plus xm. Similarly, q minus xm equal I d minus xm. So that fits precisely what we wanted here. Now there's one more thing we have to check, which is that, okay, we have to check q plus and q minus, but we also have to check q plus on psi m. So that gives me q plus acting on this, which gives me I d plus psi m. So that looks good. But it will turn out that q plus q minus this thing should give me 0, right? And I'm going to need more space. So let's say we act on plus. Well, the first one gives me 0 because q minus on psi plus equals 0. second one gives me Q minus acting on Q plus of psi plus is Q minus acting on D plus of Xm, which is not 0. It's I D plus psi minus M. So it seems we have a contradiction because we want Q plus with Q minus to anti-commute. It should give me 0, but when acting on psi plus,
I think
sorry?
sorry. I think there is a sign might be wrong on the second Q minus. No, top Q minus on X M should be minus psi minus M if this equation is the complex conjugate of the one above. I think it has a minus.
So I didn't tell you if psi plus is the complex conjugate of psi minus, but you're right. I could have. You're right. I could have done that, and that's going to give you a minus sign here, I guess. Doesn't help, but I could do that. Okay, so that's not the resolution. The resolution is that this has to be 0 up to equations of motion. So I didn't tell you what the action was for the x's, but now, in fact, you're almost stuck. The action is going to be plus psi minus So this is the action. And as you see, the equation of motion comparing to psi minus is equal to this, so you're safe. Now I can continue and check this for all the others, of course. But you can take my word for it that with this action, these transformations are going to leave it invariant up to, again, a total derivative. Okay, once again, we could do this in superspace. So we just leave as an exercise. Show that this action is invariant. That means it transforms up to a total derivative under these transformations. Now, in this case, we can try to do the same thing as before and write the thing in superspace.
Did you change that sign? You need also to change the sign in the Q minus action C minus or not? Because
So what I did in my notes is with this plus sign, this sign, okay, with this Lagrangian. I can do the, if I change the sign of psi minus, that doesn't change the action, because psi minus always appears quadratic. So I think it won't hurt if I put a minus sign.
the last Q minus acting X M no.
So
The
this one here?
lower
Yeah.
the round.
Yes?
This will change. And the round side the sign will change to sign.
If I take Q minus, let's check it.
Q minus acting on X.
So I'll have to also change the sign here. If I do it. Okay, so you're right. So, but let's leave it plus.
Sorry. The commutator of class is not two times Q plus.
Yes. So okay, here I come to the Q plus squared. You're right. So in fact, that's what I had in my notes. So. So that at least proves my point that you can't trust the filter. Okay, so the last point I want to make is about if you try to make the space-time, the world sheet supersymmetry manifest in the same way that we did before for the particle. So you will see this again with Carmen. Okay, I just wanted to give you a first view of this from the worksheet supersymmetry. So we could try to combine the fields into superspace. And you immediately see that there's a problem. First of all, you'll have to introduce not just one anti-commuting coordinate, but two, because we have two space-time supersymmetry. Worldsheet supersymmetry. So this is a spinner for the worldsheet, so it has two components, which means when we expand, we now have more terms. We have xp of tau c. So now you can expand capital plus, you can have capital plus. So it's natural to think of this one as psi, one of the psi's, and this will be psi minus. And the other one will be psi plus. But now you see there's one more term you can construct, which is capital plus, capital minus. You can't have more than this because capital plus squared is 0 and capital minus squared is 0. But you have one more term, which I'll call f tau c. So of course, this is bosonic. These two are fermionic, and this is bosonic. So somebody could have already complained to me, why do I have psi plus and psi minus, but I only have one bosonic field? They could have said, well, I thought supersymmetry means you have as many bosons as fermions. And in the particle, that was correct. Well, if you look at the equations of motion, the equations of motion for x are d plus d minus xp equals 0. And the equations of motion for psi are d minus psi plus p equals 0. D plus psi minus p. Well, supersymmetry does not imply you have an equal number of bosons and fermions. It implies you have an equal number of physical bosons and physical fermions. Well, or in other words, on shell, bosons satisfying the equation of motion. Well, this is a field which is harmonic, so this means xp can be written as a function of right moving and left moving. So let's call them f tau plus sigma. F, let's call it f tilde, tau minus sigma. I guess I didn't. So this is the general solution of this equation. Whereas these equations only have either left movers or right movers. So let's call this A tau plus psi sigma. And this would be tilde tau minus. So you see, using equations of motion, you have an equal number of bosons and fermions. For each left moving boson, you have a left moving fermion. For each right moving boson, you have a right moving fermion. So supersymmetry only implies that the equal number of physical or on-shell bosons. However, there are certain cases where you also have an equal number of off-shell bosons and fermions. So for the particle case, we had an equal number of x's and psi's even without using equations of motion. In that case, you can make the supersymmetry manifest. Because, let me finish there. So for example, I was able to write this action in terms of x. Now when we go to 2 dimensions worldsheet supersymmetry, you see you don't have an equal number of off-shell bosons and fermions, but you can change the theory by adding some auxiliary fields. And in fact, using this superfield expansion, we can see exactly what we need to add. We need to add an extra boson. But this boson should not propagate, because if it propagates, it's going to spoil this. We already have an equal number of on-shell bosons and fermions. Well, we know how to do that. We just add a term to the Lagrangian, which is Fm, Fn. So the equation of motion for F is just Fp equals 0. So it doesn't affect this count. But of course, now we have an equal number of off-shell bosons and fermions. So we have a chance of making supersymmetry manifest, which we can do using this superspace. And in fact, this action can be written Now in superspace, d tau d sigma, d kappa plus, d kappa minus. You have to introduce these derivatives as before. So this is the superspace action. And in fact, the nice thing now is, suppose, this is just the same as this. But now suppose you want to couple this to a gravitational background. So we're not even doing super Yang-Mills, let's do gravitational. Well, it turns out it's trivial to do this now. You just introduce a gravitational field, GNN, which is also going to depend on this superspace X. And we just, right, this is here. So this is manifestly world sheet supersymmetric because it's written in terms of these X's. And you can show, in fact, this describes the spinning string in a gravitational background. So if I tried to write this out in terms of these, it would be a mess. Because you'd have couplings of the X's in size, and it would be very complicated. But if you write it in superspace, it's essentially trivial. Okay, so that's the advantage of trying to construct the theory in a way that the supersymmetry actually acts manifestly, in the sense that you have an equal number of off-shell bosons. Okay, he had a question first.
No, my question was just, you say it has an equal number of on-shell bosons and fermions because you have, is it correct, you have 2 degrees of freedom F and F twiddle on X, and you have A and A twiddle on psi?
And even more than that, you have an equal number of, so remember that you not only have an equal number of bosons and fermions, you have an equal number of bosons and fermions at each mass level, which in this case just corresponds to the fact that for each left-moving boson, you have a left-moving fermion. For each right-moving boson, you have a right-moving fermion.
This is the super action that you.
Yes, for the part
you were one.
Yes.
The initial expression is not the thing. There is some special expression for the integration in K?
Yes. So what's called is Berezin integration. So the rule is very simple. And it's the same rule used in quantum field theory when you have space-time fermions. It's that if you have an arbitrary function of kappa, you know that it either has a kappa or it doesn't. So there are only 2 possible terms, A and kappa times B. So this is the most general function of kappa. And the definition of this is just equal to B. So it turns out d kappa of any function of kappa is the same as just taking the derivative of the function with respect to kappa.
What about this case where you have 2 fermions?
Good. So now you have a function of both kappa plus and kappa minus. And again, you can expand it. It has these terms. And the term you want is precisely this. So it's just going to be equal to dd kappa plus. So this is a definition. dd kappa minus of that. The reason why you use this definition, which is called Berezin integration, is that it means that the expression you get is invariant under shifts of kappa. And that turns out to be related to this world sheet supersymmetry. So this guarantees that the expression you get is world sheet supersymmetry.
I have a question. If I understand well, you basically supersymmetrize the Polyakov version of the string, the bosonic string.
So Polyakov is a little bit more involved in the sense that I've already gone to conformal gauge.
Okay.
So this is just the conformal gauge action. Polyakov action, you include the contributions of the stress tensor. But it's related. It's just choosing H. So Polyakov action, I don't want to give Barton's talk, but you have a metric of the world sheet. So let's call capital I and capital Ij the world sheet. So I and j is 1 and 2. And when you choose this world sheet metric to be proportional to the just delta Ij,
Yeah.
you reduce to this.
That is right. But I was wondering if, for example, if you look at the Nambu-Goto action, basically it's related to the area, I mean the action is basically the area of the worksheet.
Yes.
So if we think in the super symmetrized version, you may get something like the volume of the super manifold or something like that.
It's a great idea, but nobody has been able to figure out what the generalization is. So there's no RNS, there's no spinning version of the Nambu-Goto action. It does not exist. There is a spinning version of the Polyakov action, but not the Nambu-Goto. In fact, let me just say one more thing. There's another version of the superstring called Green-Schwarz, which Polchinski ignores, but obviously Green-Schwarz and Witten do not ignore. And in that case, there is a Nambu-Goto version. So it's something about worldsheet supersymmetry, there's a conflict with Nambu-Goto.
So I'm a little confused because I thought that the constraint CMXM that comes from the Nambu-Goto version of the superstring of the fermions in the Nambu-Goto.
There are no fermions in Nambu-Goto.
Okay.
Nambu-Goto is just the area. I don't know how. So I think Barton already wrote down the Nambu-Goto action. There are no fermions there. Now, if you go to the Polyakov action, you can put fermions in. And you're right, the Gravitino, the Polyakov action, it couples to the worldsheet metric, and it also couples to the worldsheet Gravitino. So let's call it chi. It has a worldsheet vector index, but it also has a worldsheet spinner index. And if you vary with respect to h, you get the stress tensor, dx dx. And if you vary with respect to the worldsheet Gravitino, you get this psi dx. Okay, so it doesn't come from Nambu-Goto, but it does come from Polyakov.
Ah, finally. Can you please repeat the statement for the last equation?
The last one?
Yep.
Yep. Okay, so this action here, I'm contracting the indices here with the Minkowski metric. Now I can go back to the bosonic string. And now instead of contracting the indices with Minkowski metric, well, if you want to put in a gravitational background, obviously you should contract with the metric of space-time. So this is the Polyakov action in conformal gauge contracted with the metric. You could do Nambu-Goto for this also. It's just the square root here, instead of having dx dx contracted with Minkowski, you contract with GMNX. So writing Nambu-Goto action gravitational background is fine.
So that is like a super metric?
No, this is just ordinary metric.
The one in the bottom.
No, this is also ordinary metric. So the only thing is, so now you want to worldsheet supersymmetrize this. The same way we did the particle. Remember the particle, we coupled this way. This was the coupling of the world-length particle to an ordinary Yang-Mills or ordinary Maxwell field. Not the super Maxwell field, Maxwell field. So we're doing the same thing now, but we're coupling to an ordinary, I should call it small field. The only thing we're doing is we're replacing this X by a worldsheet superfield X. But it's not changing the field here, it's just changing what it depends on. And these are now obviously depending on the capital A. So it's coupling to ordinary metric, and in fact we don't know, using the spinning string, how to couple to either the Gravitino of space-time or Ramon-Ramon field. So we only know how to couple the spinning string to an ordinary metric, or the B field. We don't know how to couple to the other field of supergravity, 10 dimensions.
Yes, but I think that the question is already the metrics originally depend only on the volumes of space-time.
Yeah, okay, there's a confusion. Let me tell you, let me do the particle case first, because that will explain this also. So what do I mean by this? So X, remember, is a superfield. This is infinitesimal, because this is a Grassmann coordinate. So this is of course equal to AM of x, small x, plus capital psi. And now we can expand this. So this is equal to AM of x plus kappa psi p dp. These are equal. You see that it only depends on the gauge field, but it couples, doesn't just have this term, you also have this term. And it's similarly for the metric. You get derivatives of g, which involve the Christoffel tensor.
We have just 5 last minutes.
I think I've already given you enough material. Questions? Okay, so please try to do the exercises and feel free to ask me questions and talk to Greg or